So we can use polynomials to help us model problems. And so it's good to understand just which polynomials are good for what though. And this is not exclusive, but in general, linear equations are really good for problems involving rate because the slope is a rate. Okay, so problems involving rate often are good for linear relations. For quadratics, okay, they involve a quadratic, so power 2, and they're often good for dealing with problems of area because area uses units squared as its area, okay, as its measurement. So quadratics are good for area problems. They're also good for max-min problems because we often have maximization as a vertex. Okay, and we want to often find these vertices. Cubic problems or cubic functions are good for problems involving cubes or volume. Okay, so when we deal with a volume problem, there's a good chance the model we're going to end up using is a cubic function. So let's take a look at the box problem. This is a fairly typical problem. We have a piece of paper. It's 20 by 30. And we're going to make a box from this. Now to do this, we need to kind of cut out the corners and fold up the sides. Okay, so we're going to get rid of these corners here. Okay, and these flaps kind of fold up and make the box. So that's an open box. And we want to know what the largest possible box that we're going to make is. Okay, well, how do I go about doing this? Well, what is the volume of a box? The volume of a box is length times width times height. Okay, so length times width times height. So in this picture, what is the length, width, and height? Okay, so imagine folding this box up, and really these tabs that get folded up, really we can just say is a height. Okay, and let's just call that x. We're going to call that x. Okay, and I'm going to make a table here. My height, which is x. And put in brackets x here. My width. And what's my width going to be? Well, if I take a look at this width here, this width in here, if I start with 20 and I take away x from both sides, I end up with 20 minus an x from both sides, so 2x. Okay, so there's going to be my width. So same with the length here. The length is going to be this edge here, which would be the same as this edge here. And to get this, well, I started with 30, and I want to take away, I'm just going to move my 30 over to this side. And so I'm going to take away 2 of these lengths here to get the length. So I'm going to take away x from both sides, or 2 x's. Okay, so this x in here and this x in here. So there's my height, length, and width. Okay, so let's plug in some numbers here and see what we get. So I get 1 to cut off just a little corner, 1 centimeter. My width ends up being 18. My height ends up being 28. Okay, so let's see here. Let's multiply this all together, and we can get our. So this is my length here, and then I have a volume. Okay, so this is going to be my length ends up being 28. Well, this is 50, isn't it? So we got 50 here. So it's going to end up being 48. Okay, so the volume that I end up getting here, if I do 1 times 48 times 18, it looks like it's 864. Okay, so that doesn't seem like that good a volume. In fact, if I just cut off a little 1 centimeter corner from there, it's probably not going to give me the biggest box. So let's maybe cut off a little bit more, cut off 3 centimeters. And then the width here is going to be 14. The length here is, I've kind of got it backwards, so this is supposed to be a longer side. So that's going to be 44. Okay, and in fact, let's change our diagram here. Let's just change that to 50 minus 2x. And let's say that that was the length of 20, so it makes our diagram look a little bit better. Okay, so 44, and multiplying those together, I get 1848, so that's quite a bit bigger. I'm going to go even bigger. I'm going to go 18, I'm going to cut 6 off the corners. Now if I cut 6 off the corners, now it's starting to look kind of narrow this way, because I'm going to end up with 8 centimeters here. This is going to be 38 centimeters there. And if I multiply that together, I get 1824. So that's, yeah, I've now started to get smaller. Maybe I'm going to go a little bit somewhere between 6 and 5. So I'm just kind of narrowing in on my equation here. Okay, my dimensions that are going to give me the biggest width. Ooh, 2000. So that's the biggest so far. So I'm going to just say, I'm just going to stop here and just say it's about 5. Okay, now that's not necessarily the biggest. Now, what the problem, we're probably actually not going to be able to find the biggest algebraically. In fact, we can't. This is finding a vertex. The problem here is what is the model for this? And this is what it's important to understand. Can you come up with a model to the equation that models this problem? Well, what is the volume calculation? The volume is length times width times height. Well, I can make this a volume problem with a variable x. And I can replace the h with an x. And I can start to generalize. My width is going to be 50 minus 2x. My length is going to be 20 minus 2x. And now what I've done is I've come up with a model, a polynomial model for this problem. Now, I cannot solve this algebraically, but I can graph this. So we can actually find the solution to this problem by actually graphing this function. Okay, so just to be clear, there's no algebraic solution to find vertex. If I want to find the maximum volume, I'm going to graph this and find the maximum from my graph. Okay, so let's graph it and see what it looks like. Just going to put a little graphing window here. Okay, and this graph, well, we do know a little bit about this graph. We know this has got a 0 here. It's also got a 0 at 10. Okay, and we've got another 0 way out here at 25. And it's going to look something like this. It's going to go up, it's going to come down, it's going to come back up at 25. Okay, somewhere around there. Okay, it's going to shoot off there, it's going to shoot off there. And really what we can say is, for this particular box problem, we know that our domain is going to be between 0 and 10, because if I cut off too much here, I'm not going to be able to get those other parts. So I'm just going to highlight my domain, and let's see what the solution to this is. How close was I when I'm guessing the solution is cutting off 5 centimeters, or my x is equal to 5? Okay,